Where's Mom? Because I can't do anything after I get this meeting. You and Dale's phone over my house again. In bed.
Oh, I don't know. Probably by next week, I think. Not sure. All right, children, write this down.
We're not doing kayak tomorrow, right?
I didn't see anybody bringing
Yeah,
kayak.
let's do it next week.
Yeah.
I'm leaving at 9:30 tomorrow.
You said to come to school?
I want to come to school. I want to be laying in bed all morning, like panicking, throwing up and stuff. I'm not allowed to eat like 10 hours.
Alright, so as it says at the bottom, unstable nuclei are radioactive. Stable ones are not radioactive. This makes sense, right? I told you guys that radiation comes from changes in the nucleus. So if it's changing, that means it's unstable. If it's stable, it's staying the same. So that's what we're going to talk about today. What makes a nucleus stable or unstable? Today is the 5th of June.
Wait, can you give me like a minute? Because I just got my notebook out.
I know. Next question is why did you choose to
Because I was looking for a pen, but then I'm stuck with this.
We used to make it so much easier. I can do what I want. I can.
I'm just being we consider talk.
Sorry.
Good.
Not your fault, she wasn't ready.
You're right.
There was waste of time that causes you. Alright, so there are 1,500 known isotopes. Remember, an isotope of the same element is an atom of that element with a different number of neutrons. So you could have a carbon atom that would have 6 protons and 6 neutrons. You could have a carbon atom that would have 6 protons and 7 neutrons. You could have a carbon atom that would have 6 protons and 8 neutrons. So the number of neutrons changes, but the element stays the same. Those are isotopes. So there's about 1,500 known isotopes. Now you know there's about 110 elements in the periodic table. So that means each element has, somewhere around 10 to 20 isotopes. Some isotopes are stable, some are unstable. So you see most of them are unstable and about 279 are stable. Which means there's 279 that are not radioactive and about, I guess that's 1,200 that are radioactive. So again, throughout this whole slide, I'm going to talk about isotopes, so make sure you understand. Atoms of the same element with a different number of neutrons. By the way, these 1,500 isotopes, that's what's on this list here. This thing's hanging on the wall if you ever get bored and have no life and want to look at it. It's got all the known isotopes as of 1970 or something. I guess a little old. Ready?
No.
All right.
Let's try and do it quick.
Alright. I'm going to go on. Okay, so rules for nuclear stability. There are 5 rules that I'm going to give you so that you can look at an isotope of a particular element and guess whether or not it's likely to be stable. Some of them are very easy, like the first one. Atoms with atomic number 83 or greater. So 82 is lead on the periodic table. 83 or higher, they're all radioactive.
What just happened?
Huh?
What just happened?
What do you mean?
Come back.
This one?
Yeah.
Oh, you didn't finish this?
Oh,
Okay.
go ahead, keep going.
Yeah, you can just write the top one. Rules for nuclear stability, right?
Yeah.
So, well, you can write that, whatever. How long too fast?
Yeah, you can change it.
Okay. All right, so rule number 1. 83 or higher, they're all radioactive. So that means up till lead, they may have stable isotopes, but then starting with bismuth, everything above that has no stable isotopes. So that means, radium, astatine, thorium, uranium, plutonium, all of them, there are no stable isotopes. Every version of that atom is radioactive. Got that? Next one. Even numbers of protons or neutrons tend to be more stable. So obviously if you have even numbers of both, it's even more likely to be stable. Odd numbers of both are more likely to be unstable. Okay, so here's an example to look at. Oxygen is atomic number 8. Atomic number 8 means it has 8 protons. Since it has an even number of protons, it has 3 stable isotopes, oxygen 16, oxygen 17, and oxygen 18. On the other hand, fluorine, atomic number 9, has 9 protons. It only has 1 stable isotope, fluorine 19. The rest are all radioactive. Make sure, I know we've covered this a million times, but understand, oxygen 16, that means 8 protons, 8 neutrons. Oxygen 17, 8 protons, 9 neutrons. Oxygen 18, 8 protons, 10 neutrons, right? Questions so far? Okay, so here's the breakdown of the 279 stable isotopes that are out there. 168 of them have both even protons and even number of neutrons. 57 have even number of protons, odd neutrons, 50 for the other one. And out of atoms that have odd protons and odd neutrons, there are only 4 known stable isotopes.
Is this the rule?
This is still part of rule number 2.
Are we writing them box then?
Yes, write it down. Write the table down. Because the rule is the same. So just really the tables which we got. Any questions? Am I going too fast? Everybody know what we're actually talking about here? How many people actually understand what this is all about? Alright, so what I'm trying to explain to you today is how you can tell by looking at an atom, if you know its atomic number and its atomic mass, how you can know if it's stable. Or if it's not stable, the other choice would be radioactive, right? It's either stable or it's radioactive. So what I'm telling you is even atomic numbers and even numbers of neutrons makes it very likely they're stable. There's 168 different isotopes that are stable that have even numbers of both. Odd numbers of both, there's only 4 known isotopes that are stable. So if they have odd numbers of both, they're much less likely to be stable. If they have even numbers of both, they're much more likely to be stable and not radioactive. Alright, this is a periodic table. This shows you for each individual element how many known isotopes there are that are stable. So for hydrogen, it's yellow, there's 2 stable isotopes. That's hydrogen 1, which is 1 proton, no neutrons, and hydrogen 2, which is 1 proton and 1 neutron. Now if you look at this middle section, the transition metals, this really illustrates the point of the last rule. These 3 here, 21, 39, and 57, they're orange. They have 1 stable isotope for each of them. That means 1 certain number of neutrons that works with the number of protons to make them stable. All the other versions are unstable. If you look at this next row, 22, 40, 72, this one has 5 stable isotopes, this one has 3, this one has 5. So with the even number of protons, there are many more stable isotopes. These are all odd numbers. There's only 1 for each. They're all orange. These ones, that's got 3 stable isotopes. That has 6, I think, right? Is that the color? And then that's got 4. So a lot more stable isotopes to go. Notice there's a couple oddballs, right? 43 and 61. They have no stable isotopes. I mentioned them at the beginning of the year. These 2, they are not found in nature because they're radioactive. They don't exist in nature. Now, rule number 3, atoms with the proper ratio are stable. And the thing is, the ratio is not the same throughout the whole periodic table. Okay, so what this is telling you is a 1-to-1 ratio, 1 neutron for every proton, is usually stable for the low numbers in the periodic table, the first 20 elements, atomic numbers 1 through 20. So let's pick an element. Let's say we pick number 10 is argon. Okay, so if you were making an argon atom, you put 10 protons and 10 neutrons together, that should be stable. That's a 1-to-1 ratio. If you had 20 neutrons and 10 protons, that would be a 2-to-1 ratio. That would be unstable. It would be too many neutrons. So too many or too few neutrons makes it unstable. But that 1-to-1 ratio, the same number of neutrons and protons, makes it stable for the first 20 or so elements. For the higher number elements, like lead or gold or mercury, those ones, atomic numbers 70 through 80, you want to have more neutrons than protons. About 1.5 neutrons for every proton. So let's look at mercury, which is atomic number 80, right? I think so. Okay, so mercury, if it's got 80 protons, then it has to have 120 neutrons, 1.5 to 1, for it to be stable. If it's too high above 120 or too far below 120, it's going to be unstable. It has the wrong number of neutrons. So then it'll be radioactive. This is, you don't have to write this down, but this is called the band of stability, and this is exactly what I showed. This line has a slope of 1 neutron for every proton. Well, down here, the dots, the stable isotopes, are right near that line, because 1-to-1 ratio works, it's stable. Up here, you have to have more neutrons than protons, a higher ratio, so it's above the 1-to-1 line. Up here, it's about 1.5 to 1. And you can look. So here's number 80, you go up here, and that's about 120 or 130, I don't know if I drew the line perfectly. So roughly 1.5 to 1, right? And in the middle, it's in between. Here, it's like 1.2 to 1, 1.3 to 1, it kind of goes up. There's another picture of stability bands. All right, magic numbers. Certain numbers of protons or neutrons happen to make things stable. These are just called magic numbers. Scientists are very creative, so that's the name that came up with it. Good. All right. Last rule, and this is again one of those just odd exception rules. I mentioned this before. Technetium number 43 and promethium number 61. There are no stable isotopes. This means if you have an atom with 43 protons, no matter how many neutrons it has, it's never going to be stable. Just write the top part. The rest of this is rule number 1. I mentioned that earlier. In fact, when we started with the periodic table, I mentioned these two, that they're special because they're not found in nature. And then anything over 92 is also not found in nature. And that should make sense. Excuse me, sorry. That should make sense because if something's radioactive, it's changing, so it's turning into another element, right? So that's why it's not found in nature. If you make some technetium, it quickly gives off radiation and it turns into some other lower number element, either 42 or 41 or something like that. All right, almost ready? Just the top, right? Just the first thing over there. Okay, that was this is basically a review of the 5 rules. Okay, so last thing, just a couple things. So what type of radiation is produced if something isn't following these rules? If it's outside of the stability band, if there's too many protons, too many neutrons, what type of radiation is produced? There's just 3 rules for this. This part will be short. Okay, so first, if the atomic number is over 83, remember that's one of the big things that makes it unstable, if it's over 83, then alpha particles are produced. Basically anything on the periodic table over 83. Radium, francium, actinium, plutonium, americium, smoke detectors. I want to know that. I hope so. Alright. Number 2, atoms above the stability band. So this means that they have too many neutrons for that band. I'll explain the example. It's up to you if you want to write it down. Just write the first rule, the rule down first. I'll talk about it. So if you look at the stability band, for the low numbers in the periodic table, the first 20 elements, we want a 1-to-1 ratio. So if there's more than 1-to-1, like, if you have magnesium's atomic number 12, so if it has more than 12 neutrons, then it's unstable and it's above the band. If it has less than 12 neutrons, it's below the band. If it has 12, it's on the band. Then for the higher numbers, right, like atomic number 80, you want a 1.5-to-1 ratio. So we need 120 neutrons for 80 protons. If it's more than 120, it's above the band. Below the 120 is below the band. Right? And everybody remembers how to find number of neutrons, right? Atomic mass minus atomic number. Okay, so this one, if it's there, it gives off beta particles. In this particular case, electrons. There's two types of beta particles. These are electrons. All right, last rule. It's it's below the stability band. It gives off beta particles. These are positrons, right? E plus is positrons. And that's it. Those are your three rules. Over atomic number 83 gives off alpha particles. Above the stability band, too many neutrons, gives off electrons. Below the stability band, gives off positrons. That's it. Questions? All right. We are done. Justine, you can turn that off, please.